Okay, in this presentation we are going to look at a reliability analysis worked example. So it says here the Weibull distribution in the question there. We will be looking at the Weibull distribution. I will sort of assume that you have seen it already and you'll be familiar with the cumulative distribution function and so on. We're also going to be using the exponential probability distribution also. Okay, so let's look at our worked example here. Reliability analysis. Consider a system with two independent components, A and B. Component A has an exponential lifetime with a mean time to failure, MTTF, of 1,000 hours. So that's important there, a mean time to failure. So essentially mu is equal to 1,000, and that means lambda equals 1 over 1,000. Okay? Component B has a lifetime that follows a Weibull distribution with a shape parameter beta equal to 2 and a scale parameter eta equal to 1,500 hours. So here are our exercises. What is the probability that component A will fail before 800 hours? So the cumulative distribution function for the exponential distribution. What is the probability that component B will fail after 2,000 hours? So the cumulative distribution function are actually really what we call the reliability function, which is the complement of the cumulative distribution function. Two questions. If the last two questions are as follows: if the system operates as a series system, both components must work for the system to work. What is the reliability of the system at 1,000 hours? And D, if the system operates as a parallel system, only one component needs to work for the system to work. What is the reliability of the system at 1,000 hours? So, first one is straightforward enough. This is the cumulative distribution function for the exponential distribution. Since component A follows an exponential distribution, that is the PDF. I'm not going to get into that. The cumulative distribution function is what we need. Capital F of t, okay, for subscript for component A. The cumulative distribution function is 1 minus the exponential of t divided by lambda, or otherwise t divided by mu, or otherwise lambda t. Okay, so lambda is 1,000. Lambda is 1 over 1,000, so there we have it there. So 1 minus the exponential of minus t divided by 1,000, so the probability of A failing before 800 hours is 1 minus the exponential of minus 800 divided by 1,000, so that's the exponential of minus 0.8 essentially. 1 minus the exponential of 0.8 minus 0.8 is 0.5507, okay? So 55% essentially. Now, probability of B failing after 2,000 hours. Just a couple of things to remember here. This is the reliability function of a Weibull distribution, and that is the complement of the cumulative distribution function, okay? So the reliability function of the component B is R of t subscript B for component B. That is the exponential of 1 minus t divided by eta to the power of B. Okay. And that's the exponential of minus t divided by 1,500 squared. So the probability of B failing after 2,000 hours is as follows. The exponential of minus 2,000 divided by 1,500 B squared. A little bit of calculator work, and that works out to be 30%. 0.3012. So on to part C. Just before we get going, just to remark upon that many engineers would look upon these problems from the point of view of the reliability function, which is the complement of the cumulative distribution function. So there's just a slight different approach here, and we're going to favor the engineer's approach as opposed to looking at cumulative distribution functions, which is probably how a lot of mathematical science students and statisticians and mathematicians would look at the problem, okay? Same approach overall, but just slightly starting in a slightly different way, okay? So for a series system, the overall reliability is the product of the individual component reliabilities. So R series T equals RAT times RBT, okay? So the reliability for series A is essentially the complement of the cumulative distribution function for t equals 1,000 hours. So t is 1,000, lambda equals 1 over 1,000, so we end up there with the exponential of minus 1. Very straightforward in this case. For the reliability function for the Weibull distribution, where B has a Weibull distributed lifetime, that is the exponential of minus 1000 divided by 1500 squared, which is 1000 divided by 1500 is 2/3. So when you square that, you get 4/9. And again, don't forget that minus sign. So overall, the reliability of the overall system, which is a series, at a t equal to 1000 is equal to the exponential of minus 1 times the exponential of minus 4 divided by 9. That is 0.3678 times 0.6411, which is approximately 23%, 0.2358. Okay, so this is the parallel system reliability. So for a parallel system, the overall reliability is 1 minus the product of the individual unreliability functions. What's an unreliability function? It is the complement of the reliability function. And what was I just saying that earlier on? That is actually the cumulative distribution function. Okay, so moving on to look at t equals 1000 hours. So the cumulative distribution function, which is also 1 minus RAT, R of t for component A, that is 1 minus the exponential of minus 1000 divided by 1000. To recall that t is 1000 in this question, whereas the rate parameter is lambda, which is 1 over 1000. That is 1 minus the exponential of minus 1, which is 1 minus 0.3678, which is 0.6322. Okay, and for the Weibull lifetime for component B, the unreliability function, which is the cumulative distribution function, which is 1 minus R of t for component B, that is 1 minus the exponential of minus 1000 divided by 1500 to be squared. Okay, that 1000 divided by 1500 is 2 divided by 3. When we square that, we get 4/9 and put in the minus sign, so we get minus 4/9. So we have the 1 minus the exponential of minus 4/9, which is 1 minus 0.6411, which is 0.3589, 35.89%. So the parallel reliability at 1000 hours is 1 minus 0.6322 times 0.3589, which is 1 minus 0.2269, which is 0.7731, 77.31%. Grand, we leave it there. A lot of work done there. Good stuff.